We've seen dynamic programming algorithms for finding the edit distance between two strings and also for finding approximate occurrences of one string inside another. In this lecture, we'll look at a couple of variations on the theme of dynamic programming for edit distance, and we're going to use it to solve two different problems called global alignment and local alignment. These are two very commonly solved problems in lots of different biosequence analysis tools, and they're both relevant for our target problems of read alignment and genome assembly. So let's start with global alignment. Edit distance penalized all the different kinds of edits that we might find the same amount, right? Whether it was a mismatch or an insertion or a deletion, edit distance would penalize that at the unit of 1. Each one of those things incurred a penalty of 1. So there was no difference, for example, between the penalty for a insertion versus a substitution, and there was no difference between the penalty for a substitution that turned an A into a C versus a substitution that turned an A into a T. So it doesn't always make sense, though, to penalize all these differences the exact same amount. So what if it turned out, for example, in practice that gaps were a lot less frequent than substitutions? Well, then it might make sense to penalize the gaps more than the substitutions. Or what if it turned out that certain substitutions, certain base-to-base substitutions, were more likely than others? That we might want to penalize them less than those others. So in fact, both of these things are the case. Some DNA substitutions are more likely than others. So for example, we can divide all possible DNA substitutions into two categories called transitions and transversions. And to understand what these are, we first have to understand that the bases A and G, adenine and guanine, both belong to a category called purines. And then the bases C and T both belong to a category called pyrimidines. And for substitutions that change a purine to another purine, or that change a pyrimidine to another pyrimidine, those kinds of substitutions are called transitions. And then all other kinds of substitutions are called transversions. And so if you just enumerate the possibilities, you'll see that there are twice as many transversions, kinds of transversions, as there are kinds of transitions. So you might think that transversions are going to be something like twice as frequent as transitions. But it turns out that in reality, if you look at the substitutions that differentiate, say, the genomes of two unrelated humans, actually transitions are about twice as frequent as transversions. So it's the other way around from what you would expect. So if transitions are so much more frequent than transversions, it seems like in our substitution, in our penalty scheme, we might want to penalize the transversions more than we penalize the transitions. Another example is small gaps, so small insertions and deletions in the genome. So it turns out that if you take the genomes of two unrelated humans and you just count up how many differences there are that are substitutions versus how many differences there are that are small insertions or deletions of just a few bases, you find that the substitution rate is something like 1 in 1,000 bases, whereas the indel rate, indel meaning insertions and deletions, the indel rate is something like 1 in 3,000 bases or so. So indels are less frequent than substitutions. So we might want to penalize indels more than substitutions. So we want to move beyond edit distance where every kind of difference receives the same penalty, and instead we want to assign different penalties to different kinds of mutations, different kinds of events. So here, for example, is what's called a penalty matrix. So this matrix has an element for every kind of penalty that might be incurred in an approximate match. Some of the elements correspond to substitutions, like these yellow and green elements, and some of the elements correspond to insertions and deletions, like these pink elements. But a key point is that we can set the elements of this matrix in whatever way is appropriate for our biological context. So if we're working with DNA and we're comparing the DNA of two different humans, then we might use a substitution matrix like this, where transitions receive a lower penalty than transversions, and then transitions and transversions receive a lower penalty than gaps. So remarkably, we barely have to change our edit distance algorithm at all in order to accommodate this new penalty matrix. When it comes to filling in our dynamic programming matrix, all we really have to change about the algorithm is we have to change the value that gets added on when we calculate the three contributions, the diagonal, vertical, and horizontal contributions. In the case of edit distance, for an insertion or a deletion, for a vertical or a horizontal move through the matrix, we just added 1 onto the edit distance of the shorter prefixes. Now we're going to add a value that we look up in our penalty matrix. Also, before, when we were considering a diagonal move, we would use our delta function, basically to figure out whether the characters from x and y were equal, in which case the delta function evaluates to 0, or whether they were not equal, in which case the delta function evaluates to 1. Now we'll just, again, do a lookup in our penalty matrix to determine what the penalty should be. So apart from this, the algorithm is pretty much identical to the algorithm for edit distance, both in terms of how we fill the matrix and then also in terms of how we find the traceback. So that's global alignment. So here's a global alignment matrix filled in, here's a traceback. It's all very much analogous to what we did with edit distance. So global alignment is powerful in the sense that it gives the user the ability to set each of these different penalties according to the biological problem at hand. So local alignment, on the other hand, is a somewhat different kind of problem that's being solved. Although surprisingly, it will turn out that the solution is quite similar still to the solution for edit distance. So in the local alignment problem, we're not trying to find the distance between two strings, and we're not trying to find occurrences of one string inside another. Here, the problem we're trying to solve is, given these two strings, x and y, we'd like to identify the substring of x and the substring of y that are most similar to each other. And we'll define more clearly later what we mean by most similar to each other. But first, let me show a quick example to motivate this local alignment problem. So here are two strings. They're in English, so that the similarities are more obvious to us. And the question is, can you find a pair of substrings, one from x and one from y, that are the most similar? So looking at this example, it seems like these substrings in the middle here are the most similar. So they're at Hamming distance 1 from each other, but they have 9 matching positions with each other. So this is approximately the kind of problem that we're solving with local alignment. Now, in a sense, this seems pretty difficult compared to edit distance, because we have to somehow consider all possible pairs of substrings from x and y. And if you just consider how many possible pairs there are, it's going to be related to the product of the squares of the lengths of x and y. So that's a lot of pairs that we might have to be sifting through. But it's going to turn out that actually the amount of work we do is no different from a global alignment problem of the same size. So here's the recurrence for local alignment here. The differences between this recurrence and the recurrence we used for global alignment are highlighted here in red. And instead of using a penalty matrix, we're going to use something similar, which we'll call a scoring matrix, which is shown in the lower right. And an important difference between the scoring matrix and the penalty matrix is that in the scoring matrix, we're going to give a positive bonus for a match, and then we're going to give a negative penalty to all the different kinds of differences. So in this case, substitutions are going to have a penalty of -4, and gaps have a penalty of -6. So now if we use this recurrence and this scoring matrix to fill in a dynamic programming matrix, we'll get a matrix that looks like this. And you'll notice immediately that many of the elements are 0. So intuitively, this is because the goal of local alignment is to find parts of x and y that match closely enough that they sort of pop out from the background of zeros, from the background of dissimilarities. And so you'll see, for example, here, the values that are non-zero are mostly over here, sort of in this region here. And if we want to find that local alignment, the one that gives the best similarity between two substrings, first we're going to look for the element in the matrix that has the maximal value. And in this case, that's this 12 right here. That 12 is the maximal value. And that corresponds to the optimal local alignment. And then if we want to know which substrings are involved in that alignment and exactly what the shape of that alignment is, we can use our usual traceback procedure. So we'll start in the cell that's labeled 12. We'll do our usual traceback thing. The only way that we'll modify our typical traceback procedure is that we're going to stop as soon as we reach an element whose value is 0. So once we've done that, first of all, we've figured out which are the substrings from X and Y that are the most similar. They're highlighted here in green, so here's the substring from Y, and here's the substring from X. And we also know the shape of the alignment between those two substrings shown here. So this is a very useful tool. Both global alignment and local alignment are very useful tools, and they're used in many different kinds of biosequence analysis tools, including in read alignment tools and assembly tools.